Okay, Professor Lewis, and we're going to be talking about hardness testing. And when we think about hardness testing, it's basically a penetrator that's going to go into a sample. Now, sometimes we measure the depth of penetration. Sometimes we measure the width of the indenter that penetrated the material. And a lot of times this is going to leave a permanent mark on the part. So this can be considered maybe a destructive test. The part may still be usable, but you do have a localized damaged area in that area. So if you have a seal or something on the part, you may want to test it in that area. So let's talk about the relationships of hardness to properties. If I was to go to the grocery store and look at somebody's cart, I might could estimate their family size, their social habits, a lot of different things about that family. Likewise, if I look at the hardness on a material, the results, I can get the strength, the machinability, all these different aspects and properties related to that material. So this is going to be a real powerful tool in this course in terms of understanding the properties. Now, doing a quick understanding of hardness testings, we could have a penetration test versus a scratch test. Now, scratch is cheap and crude. It could be something as easy as a file, which is going to be around a Rockwell 60C. And it could scratch the part. And so we could have Mohs scale, and we'll talk about that here in a minute. We have the penetration test, which is going to be a lot more accurate, a lot more precise. That's going to be our Brinell's hardness Vickers type test. And so it's going to be a little more expensive, but this is what we're primarily going to see out in industry. Now, when we talk about Mohs scale, this is a scratch test. We could have different minerals, talc being the softest, diamond being the hardest. So a scale from 1 to 10. And it's not so much of a linear progression of the minerals, but it does let us see relative how hard is something compared to each other. So diamond is going to be very hard. We could have another scratch test where we can actually get files that are heat treated to different Rockwell C values, and you guys will learn what Rockwell C values as we go through there, and we can actually scratch a part. So if we were to take a part and take a file across the part, we might have a part that's soft and annealed, and it would leave a nice little gouge in there. If it was hard, then it might just zip right across that part and not cut into it because this may be close to the hardness of the file. Now, Brinell is the big bulldozer of penetration test. What we're going to have is a penetrator that is going to be 10 millimeters in diameter. It's a 10 millimeter ball, tungsten carbide balls typically, and we're going to put 3,000 kilograms load. Now, for our English speaking people here in America, we like to think of that being about over 6,000 pounds here. That's a lot of weight on that ball. So we're stresses, we're putting a lot of stress, and we're going to deform that material, and it is going to make a nice little crater here around that material, and that's going to be a permanent mark. So it's basically just a big hydraulic press. We're going to press that ball in there, and again, they have a standard. We talked about how to access those standards in other videos. We're going to put that on there for a period of time, and it's going to make that indentation. And then our machine, we're going to have a microscope in which we can measure the diameter of the crater that was made in that part. Now remember, that's a crater. That was raised material, so we can only take those measurements on one test, on one side. Now this is for thicker parts. The microscope is going to let us measure the diameter of that indentation. We're going to take that, and in the ASTM standard, they'll have how to interpret the ball diameter. There is an equation, but the easiest way is just to access the standard and go look at the diameter of the impression and get that to a Brinell number. Now, Brinell numbers, and something you want to make a note of, are going to be represented as BHN numbers. So if you see a 600 BHN number, that's going to be some pretty hard material here. This is quench hardened steels here. If I see something down around some brass, it's going to be down, and that's going to be soft material, 120 BHN. And so I can see the different materials that we have. So again, BHN numbers. When we look up our material properties in MatWeb, sometimes they might list something as BHN, and we're going to have to convert, especially when we're looking at the heat treaters guides in terms of tempering and stuff. They won't always have Rockwell B, Rockwell BC. They're going to have Brinell, Vickers, and we're going to have to convert. And there's an episode on how to use the links and access that. And we'll even talk about that again here towards the end. Let's go keep on this rather smartly here. We have a Rockwell testing. This is our machine in lab. We have a round part. We have the correct anvil in, taking a hardness. So we're going to have to do a roundness correction factor on that. Now, what is a Rockwell hardness test? A Rockwell hardness test is basically going to be in lab, we're just going to access two scales. There's a lot of different scales within those, but in lab we need a Rockwell B indenter. It's a 16th inch diameter carbide ball. And then we have a diamond indenter, and that's the C scale. And the C scale is going to use a 150 kilogram load. The B scale is going to use a 100 kilogram load. What we're going to do is put a minor load, so about 10 kilograms of that load we're going to put onto it initially, zero it out. We're going to push in for a certain period of time. It's going to measure the depth of the penetration from that reference line, and it's going to report it back in terms of Rockwell values. Now, this test compared to the Brinell, this is measuring depth of penetration, where the Brinell is measuring the width of the penetration made. And again, this is going to use ASTM E18. Rockwell scales. When I look at Rockwell scales, I told you that we're going to use B and C. So B is for soft metals, C is for hard metals. If you have a piece of metal and you don't know what it is, so if you're going to start testing on a material, always go with the C scale instead of the B scale. If the C scale doesn't work, it'll drop off the charts. We'll talk about what the minimum values are here in a minute, down around about 20. We're going to move over to the B scale then. The reason we do that is if you have something really hard, you could damage the penetrator used for the B scale. Now here's a list of a lot of different scales within the Rockwell area, and it shows the loads with the minor and the major for the total load applied. So here's our B, 16th inch ball, minor load is 10, combined is going to be 100 kilograms, so we would have to set the machine for that. C is going to be a diamond cone with 150 kilogram load. Know those loads for the different indenters and the types of indenters for the different scales. Now, in the standard, we're going to see that when we compress that material down, we're going to have these nice little craters developing, and we've worked that material locally in here in the substrate base material. And so we don't want to have, we want to take in consideration two things. How close can I take another measurement from the next? In the standard, it's going to be 3 times the diameter of the indenter. That's going to get us to some new material to take our test. The other thing, likewise, is we don't want to get too close to the edge, so 2.5 times from the edge. So be careful about how you measure and make your measurements on there. Some of your samples are going to be small, and you're going to have to be smart about how you strategically place those measurements. Sometimes you have to take 3 or 4 measurements on a fairly small sample, and it can be done. You're just going to have to lay those out. The other thing is minimum thickness. Some parts we don't want to be testing the properties of the anvil under here because we are compressing and testing the material properties. So in the standard, we'll show you guys that where you can find that in terms of minimum thickness for the parts. Now, testing on a part, you're going to put your part in here. Make sure that it is flat and level and burr free, and then come in and take your measurements. And we talked about that raised material again. We'll have calibration standards in the labs, and typically the TAs and everybody in the lab will calibrate the machines. You guys won't have to do that. These cost about $126 a pop, and after they get full, we have to pitch them. And we only take measurements on one side. So if I was going to heat treat a part that was, let's say I was making knives and I wanted a Rockwell C of 50 to 52, I would probably buy a calibration standard for 50. And then I would check that before I go measure my parts so that I'm closing the gap and not having a calibration standard that's way off. And that becomes part of my ISO procedure possibly. We have different anvils for different type parts. This is going to be for round anvils. And again, I'm going to have to apply correction factors for that because the results are not going to come out the same if I test on a flat surfaced part. Here's a flat surface anvil. So we want to make sure the connections here between here are going to be clean when we put these on. So take a rag and we'll clean those off. Now, roundness correction factors, we'll see where we pull these up in the standards, but basically we need to make sure we're dealing with, are we dealing with concave or convex surfaces, and get that correctly. And then we need to make sure we're reading if we're on B scale or C scale, and then we're going to have to take in consideration the diameter of the part, take the reading that we have, and we're going to add the values that we see in the lining up of the rolls in the column. And so that's going to do that. Now, will our machines do that in lab? Yes, they will, but we turn that off because a lot of people forget to turn them off, and then people are getting data that's 5 or 10 points off, and we can't have that because that's a huge difference in the results. Later on in some of your labs, you guys may be using a Jominy test attachment, and we'll talk about that, and that's going to let us take hardness values across a part like this. Now, when we talk about other tests, there's Knoop and Vickers. and this falls under this ASTM standard. And basically, Knoop has an elongated diamond here versus the Vickers, which is going to be this type of diamond and dinner. And these are going to be for a lot finer. We can get down even to the grains of the metal. This is going to have like a 4 kilogram load, for example, on some of these. And there's different variations of these tests. But in essence, this would be what we call micro hardness testing. And in this, we can put our part in here. And so we've got little micro knobs. We can adjust the slides on here. And we're going to be able to come in there and put our indention on there. And it's going to be very small. And we're going to measure the overall widths of those, height and length, and then interpret that into data as well. So we have Vickers test. Now, if you're doing rubber or plastic, we have what we call a durometer. That's just going to be a penetrator that's probably not going to leave a permanent mark because this material is resilient. It's going to pop back. And basically, we're measuring the depth the penetrator goes in there, and it's going to report it to us in Shore A values. So here we have some Shore A values here, and this is a smooth on. It's a rubber type manufacturer that sells silicone rubbers that we can get different types, and the materials are going to have different hardnesses, different flexibilities, and we can do that kind of measurement. Here's a hardness conversion chart, and we're going to look at that later in the standards here in a minute. And so what we would need to do is maybe go from a Rockwell C over here, if I can get my mouse woke up, there it is, a Rockwell C to a Brinell number to a Vickers number. Okay, one last thing I wanted to talk about, and we have a video out there on links and how to access Compass to get to the ASTM standards. And what I'm looking at is the ASTM standard E18 for Rockwell hardness testing of metallic materials. And what I want to point out is when you go through here, there is a link down here for hardness conversions to different tables. If you click on that again, it's probably going to take you to something to say you need to buy it. What I would do is do a search in Compass here for E140. And what that's going to do is bring you up to this standard right here, which is E140. And you're going to be able to go through this and find a wonderful conversion table. And what I'm going to do is circle up on this so we can talk about this table here in a minute, because I really like the orientation of this one better than the previous one I showed you. This, and we have copies of this at the machines for you. And so if I'm looking at Rockwell C 60 values are really, really hard here. Again, it's going to reference my Brinell numbers over here with the different carbide balls that we have. Remember we talked about 600s being very hard? Yeah, we're starting to see that. I can also get my Knoop and my micro hardness values off of here. Now, if I come down here and I go down this table to Rockwell C20, now let's look at the Brinell numbers. We're talking around 240-ish right here, just a little under 240, 226 here. Rockwell C20 is the minimum value we're going to measure in lab. Now, there are going to be some times when we do a Jominy test that we'll probably go all the way down to a Rockwell C5 or 10. That's okay, because it's hard to say, let's convert from Fahrenheit to Celsius. It's two different scales. B and C is going to be different scales. And so on that one test, we might can get all the way down to Rockwell C5, and it kind of gives us a progression that it's really going down in value. But most engineers will stop at a C20, and then they're going to convert over here to the B scale. And here's our B scale values. Now, we were talking about the Brinell values of 240. If you notice that, we can see a little overlap of the two scales from B to C on that Brinell number as a reference there. And we can see that Brinell numbers, or Rockwell B numbers of 90 are going to be hard on its scale. It's on the very soft side of the C scale. That's why we always start with the C scale and then go to the B scale, and then we go on down to the very soft materials. So that's kind of, in a nutshell, the Rockwell hardness testings on these. One of the things I wanted to point out also about and we're in the ASTM standard here for Rockwell testing. If I cursor down here, there's going to be a lot of information in here in terms of the testing method, how long, all that fun stuff, and you can read through these. There are some important things that I always like to point out to everybody within the standard, and I'm going to just keep cursing down here. Here's that reference. We talked about placement of our indentions on our test samples, so it talks about that. This is going to talk about I think in the video on the using of the machines, I'll talk about the calibration blocks. Different calibration blocks have different amounts of errors that we can read, and so typically, if we're within a point to 2 points on a calibration standard, we're pretty happy. Again, we would want to look at, are we on this, and is it a hard material, soft material? The Rockwell C, we can have a little variance there. So we're complying to these kind of ASTM standards. And so if you go to industry, you're going to want to get these standards and go through these things. And you can tell there's a lot to this about temperature, all the various things that you're going to need to do. Okay, if you keep on scrolling all the way down here, I mean, this is quite a ways down here. We're on page 26, getting down around page 27. We're getting into the minimum thickness for different scales. So what we're saying here, here's our Rockwell C scale, here's the anticipated value, and here's the minimum thickness that those parts can be before we start testing the properties of our anvils. And it's going to tell you for the Rockwell Bs as well. Now then, down around page 30, we have the correction factors for convex surfaces, so things that are round. We also have them for convex, concave type parts. And again, this is the ASTM standards talking about the dial reading, what we measure, and the diameters, and what we need to add to those. So all that comes directly from the ASTM standards. Now we're at the lab, we're going to have the hardness conversions printed out and laminated for you, as well as the roundness correction factors for you, because you will be working with round and flat objects. Well, I hope that helps you out understanding Rockwell testing. Go learn how to use that machine the next video, and then you'll be ready for lab.